Thank you. I'm going to talk about two debates that we have in exoplanet science that come from the distribution of planets. Now, planets are a little bit like bumper cars, but they scatter without touching. The first debate comes from having found planets that are too close. That there seems to be an excess of planets in of hot Jupiter, of giant planets, in the one-day period range. And so people have postulated that perhaps the tidal migration is unexpectedly weak. I don't believe that tidal migration has to be weaker than has been measured for binary star studies, because okay, here's the excess for giant planets, but here's the excess for medium planets. There's not really an excess for medium radii planets. So instead, I propose that it's reasonable to think that there's an ongoing migration, a larger ongoing migration of giant than medium radii planets. Because for the medium radii planets, you don't need to have such weak migration, or such weak tidal dissipation. Another way of looking at these same statistics is that if you take the fit here, and this is the data, and so the Kepler data here is kind of rough, but if you plot for different strengths of tidal dissipation, what you would expect is that you would have a fairly continuous, ongoing amount of planets going into the star. So you would expect, other papers have done measurements that tidal dissipation is weaker than a Q of 10 to the 7th. That it is a higher number than 10 to the 7th. But I say that that these numbers here that appear to be sloping, if you just have new planets coming in, filling in this gap, you can have stronger tidal dissipation without having to claim that the tidal dissipation for planets is weaker than for binary stars. And then I show it this way. This is the rate that you would need to fill up the previous gap. So if you take what you would need to make this constant here and plot it as a strength of tidal dissipation, you only require on the order of one giant planet per star per gigayear. That can reasonably be supplied by planets going out. So I'm glad that we had an earlier talk, and that's why I asked the question, do you believe that planets can still be migrating in after the disk is dissipated? The Kozai migration, planet-planet scattering do not require the presence of a disk. The second debate, I'll go over all the words, is where does the planet metallicity correlation come from? Previous authors have thought that there wasn't a correlation between the eccentricity of the planet and the metallicity. But Rebecca Dawson and I have found that there is in fact such a correlation. Here's some statistics to go and show it. Also found some interesting correlations that the population of planets with high metallicity and low metallicity are dramatically different. Several differences. Now, while I'm promoting planet flow going inward, I've also found that if there's a binary companion, that the metallicity is higher. This would argue that for the formation. So we have this debate between, does the metallicity come from formation or from pollution? Here again, statistics showing that with binary stars, it probably means that you have to have higher metallicity in the beginning. So here, Rebecca Dawson, she showed that you have the pileup has to do with metallicity, and this is an earlier result showing that it's been known for some time that there's a metallicity stellar mass correlation, and then I show it here where I separate out with the colored dots. For higher eccentricity systems, you can see this correlation is even a little bit stronger for the filled-in dots for eccentric situations. So So this sort of work can come from having like 1,000 planets, a few thousand Kepler candidates, and it's important that we all have put into finding these planets. I'm glad that when I worked for Las Cruces Global Telescope that I contributed several papers, and so we've got about 1,000 planets. So I've got these 2 debates and hope to see how they resolve themselves, and be glad to have any questions, and maybe afterwards we can discuss this a little more, trying to put 2 debates into 5 minutes is a challenge.
Yeah. All right, thank you. Any questions?
Sorry, I'll ask an ignorant question. Are you saying that through Kozai and then tidal capture you get inside the synchronous radius and then you evolve inwards toward the star? Or that you have something more direct where you go directly into the star?
I'm not focusing on the mechanism. I'm saying that there are planets that are closer into the star. There's also evidence that stars have been polluted. Well, I guess I am saying a little bit something about the mechanism, that when you have eccentric planets that you, I see some evidence that other planets have gone in and polluted the star. So whatever the mechanism is, that there's some pollution associated with that. But whether it's Kozai or whether it's planet-planet scattering, I'll leave that for the theorists to describe how to get this flow.
If I understand correctly, you assume something like a planet infrared of, I think you said 1 giant planet per star per gigayear, something like that, right?
Yes.
That would probably mean that you need protoplanetary disks to be able to form multiple giant planets when you look at the current detector planet statistics, right? Is that supported by current planet formation models and disk models?
We have systems with multiple giant planets found by Kepler.
But they're not quite common, right? What is it? Did you estimate what your typical giant planet formation number per system would need to be in line with the observed numbers of giant planets in close orbits that we see right now?
That's actually what my next proposal is to try to quantify that. But I do think that the fraction of stars with planets is quite high, and I don't think that rate will decrease the current population by all that much.
Any other questions? All right, let's thank Stuart.